Here we have a short video over solving linear systems with matrices. So more specifically, let's talk about a system of two equations. Say we have our following systems here, ax plus by equal to e and cx plus dy equal to f. We could turn this system into matrix form, given the following. We could have our what we call the coefficient matrix, which is all the coefficients from our system, with elements a, b, c, and d. We can have our variable column matrix with x and y, and then our constant matrix, which is another column matrix of e and f. And we know that this can work out because if we follow our matrix multiplication, that if we were to take a times x, we will get ax back, and then b times y, we're supposed to add that, and that's where by would come from. So that does fit our matrix multiplication, and once again, we could do cx. To get cx, and then add to it d times y plus the dy. So that does follow all of our matrix multiplication. So we could take a system, throw it into this matrix form. So I can label this coefficient matrix as A. I can do the variable matrix as X, and then our constant matrix as B, that it's equal to B. Now, from previous videos, we had talked about inverses, that we knew that if we could multiply a matrix by an inverse, if it does exist, that it would cancel it out. So what I can do then from this is, what if I go ahead and multiply both sides by the inverse of that matrix, since it's supposed to exist? Well, here we have A inverse times A. We know that that's supposed to give us our identity matrix back. But an identity times another matrix, we know, is just the matrix itself. So what we can conclude here is that the solutions for x and y, that column matrix for our variables, is just going to be equal to the inverse of our original matrix times the constant matrix. So what we can say in, the solutions to the given linear system, x and y for us, can be found by multiplying the inverse matrix of A, labeled A inverse, by the constant matrix B, or what our constant matrix is, or whatever our system would be equal to, those two numbers. So let's go ahead and look at some steps of how we can solve a linear system with matrices. Again, we're just talking about linear systems of two variables and two equations. Step one, we need to take our system and we're going to write it into the ax equal to b form, in matrix form. From there, we're going to find what the inverse of our matrix is. And then finally, we'll take that inverse and we're going to multiply it by our constant matrix. So we got a couple examples that we'll look through. Use the inverse matrix to solve the system of equations. So here's a system of equation. We have 7x plus 5y equal to negative 14, and negative 6x plus y equal to negative 25. So first thing I'm going to do, I'm going to extract the variables, and I'm going to borrow all the coefficients on the left side and write a matrix, a 2 by 2 matrix. So we got 7, 5, negative 6, and 1. And I know the 1 is there because that's the coefficient of the 1 in the bottom equation. We have our column matrix of x, y, and our constant matrix of negative 14, negative 25. So I want to go ahead and take the red matrix that I have here, and I'm going to find the inverse of it. And to remind you, how do we find the inverse? Well, we got to determine what the determinant is of the matrix first. We can't have a determinant of 0, because if there is a determinant of 0, then there is not an inverse for this particular matrix. But I will go ahead and we will take the 7 times the 1, and we're going to multiply it by, subtract away from it whatever 5 times negative 6 is, which is negative 30, which gives us the determinant of 37. So we definitely can find an inverse here. How do we find that inverse? Well, to remind you, A inverse is 1 over that determinant, and we will switch the A and the D, and we will also change the value of the C and the B value elements in the given matrix. So 1 over my determinant of 37, trade places with the 7 and the 1, and since 5 is positive in the original matrix, it'll be negative 5, and since 6 is negative in the original matrix, we'll change the sign to 6. We will take our scalar here, because that's just a number, we'll distribute it through the matrix, and this gives us our inverse matrix. So by rule, we are now to what step 3 is, which is taking my inverse matrix and multiplying it by our constant matrix. So we'll start by taking this matrix, and we're going to multiply it through with this matrix here, our constant. So A inverse times B, or in other words, our red matrix times the blue matrix, go through our matrix multiplication, taking our row times our column and adding up their products. Take 1/37 times negative 14, add to it negative 5/37 times negative 25. That gives us a value of 3. Moving on to the bottom row in the column, we have 6/37 times negative 14, adding to it 7/37 times negative 25. That gives us a value of negative 7. So what we can say then is that the solutions to this system of equations is the x value of 3 and the y value of negative 7. So one example there, let's take a look at a second example. Here's another system. We have 12x plus 11y equal to negative 35 and negative 8x minus 5y equal to 21. Go ahead and rewrite it as a matrix in ax equal to b form. Now that we have our matrix A in red, we're going to go ahead and find what that inverse is. Determine what the determinant is, make sure that it's not 0. Taking 12 times negative 5, which gives us negative 60, subtracting away from it the product between 11 and negative 8, which is negative 88, that gives us 28. There is the number that goes in the bottom whenever we start our inverse notation. So A inverse, what is the inverse of our original matrix? Well, that's 1 over the determinant of A, equal to trading places with the 12 and the negative 5, and switching the values of negative 11 to negative 11 and negative 8 to positive 8, and distributing the 1/28. So the matrix that we have here is the inverse of A, and we're going to take that and multiply it by our constant matrix. So A inverse times B. Taking A times the B, taking our row times the column, adding up the products, we get negative 2. Taking the bottom row times our column once again, that will give us negative 1, which concludes that our x solution is negative 2 and our y solution is negative 1. So there's how you can find the solutions to a linear system of two equations using the